Okay, so this is the question I picked for the assignment. It's an organic chemistry question that deals with electrophilic addition and the Markovnikov rule. So the question asks, which is the major product of the electrophilic addition of hydrogen chloride to propene? So hydrogen chloride, you could annotate that as HCl to propene. Now the first thing we have to do is actually draw out propene to have a macroscopic view of this question and to deal with the additions and drawings of the molecules. Okay. Now the first thing we realize is that, obviously it has 3, 4, 5, 6 hydrogens. And we could deal with the amount of hydrogens that the answer provided whether they increase or decrease. And if they decrease, they're obviously wrong because they don't make sense. Because we're adding electrophilic addition. And if the amount of hydrogens decrease, that's not addition. And the second thing we realize is that this CH3 here, the CH3 group, creates an asymmetric. That's not how you spell it. Asymmetric alkene. Symmetric alkenes, however, if it was symmetric alkenes, they deal with normal electrophilic addition with the intermediate steps and the induced dipoles and electrophiles and stuff like that. But they don't deal with the Markovnikov rule. So this is another point that we have to realize in this question, is that this question deals with the Markovnikov rule. So we could have that written down, Markovnikov. And this deals with the stability rule, which I will be explaining in just a second. And this is all because this CH3 created a asymmetric alkene, which in this case is propane. So now we could put that on the side. So now when we talk about Markovnikov's rule, we know that stability increases or decreases as the level of carbocations decrease. In other words, I'll just draw it out initially. So we have tertiary, secondary, primary carbocations. The tertiary carbocation is going to be drawn as this. So we realize that we have 1, 2, 3 R groups. Now if we just draw the secondary carbocation, it's going to look like this. Now we notice that the amount of R groups decreased. Now we have 2, hence the name secondary. Now primary carbocations it's not a electron push, it's just a bond between 3 hydrogens and a carbon, and this is a carbocation, and this hydrogen here could be replaced by an R group. Now these arrows right here represents the pair of electrons being pushed towards the carbocation. In other words, it's called the positive inductive effect. And what these electrons are doing, so we have electrons, we are dealing with electrons now, they're trying to stabilize, electrons trying to stabilize the positive charge of carbon. So the R groups that they tend to push the electrons, these arrows, they tend to push the electrons towards the carbon atom which they are attached to, and this results in a tendency of stabilizing the positive charge on the carbocation right here, as I just drew. So now they're all correct. All of these tertiary, secondary, primary carbocations, they're correct. Chemically speaking, they're correct. But the more correct one, which in other words, the preferred product, should be the tertiary, because it's the most stable. Because it has more R groups. Thus, having more R groups means that the carbocation is being stabilized even more, because there are more. There's a greater push of electrons to that carbon, and the primary is the least stable. So, as I said, with that being said, and having that in mind, having more R groups means that it's going to be more stable, because having more R groups means that it's more stable, because these electrons are being pushed to that carbon cation, which is trying to stabilize the positive charge. And if we have a greater push of electrons to that carbocation, it's going to be more stabilized. So now, if we look at the answers, with that being said, we're trying to find the answer with tertiary structure, because it's most stable. But if we also have a primary, it's also correct, because in that case there's no tertiary structure, because if we have a tertiary structure, it's quote unquote more correct. So now let's have a look at A, product A. It's Cl, C, H, C, H, double bond. Well, now first thing we realize is that we have a double bond, and that doesn't apply to the Markovnikov rule, because if we have a double bond, that interrupts the stability of the carbocation. And initially the double bond actually went away because of the induced dipoles and the intermediate effects, or the transition effects that we used to draw with curly arrows and all that kind of stuff. But another reason why this answer is wrong is because 1, 2, 3, 4, 5 hydrogens. So as I said in the beginning of the explanation, if we had an answer with less than 6 hydrogens, that's a very crucial part of this explanation, or propene. If we have, for example, 5, it's incorrect, because it's an addition reaction. So we're trying to add a hydrogen. And if we have 7 hydrogens, that's one part of the answer correct. But we have to differentiate between tertiary and primary structures. That's if we have 2 of them. So now we could cancel out A. Looking at B, you could initially know that the number of hydrogens is 7, but we could analyze that further. So initially we take a look at that. We have 7 hydrogens. So we do have 7 hydrogens. But now, is it a secondary, tertiary, or primary carbocation? So now, another part of this tertiary explanation, tertiary, secondary, primary, is that energy, as I drew that black arrow on the right, energy increases as stability decreases. Because if it's least stable, it requires more energy. Well, it has more energy because it has a less pull of electrons. So now, if you look at, well, not a less pull, but a weaker pull of electrons towards the carbocation if it's primary. So, have that carbocation right here. We have a Cl group, a C here, a C here. First thing we realize is that it's a tertiary carbocation because it has 3 R groups, which is perfect to our answer. But we also have to analyze why the other answers are correct. And now we know that it's tertiary, it's most stable. Because as I said, the other answer, C could be a correct answer, but this is a quote-unquote more correct because it's the preferred product, chemically speaking. So now if we have a look at C, so now we know that B is the correct answer. Let's have a look at C. Well, if we just draw it out. Well, it's a secondary carbocation, which is also perfect, and it proves the stability explanation that I have provided. And however, if we have another look at this, if we count the hydrogens, it's seven hydrogens. So if we just have went to the rule of increasing hydrogen atoms, both B and C could have been correct. But B is more correct than C because this is a secondary carbocation right there, and it's bound to 1, 2, well, in this case it's C and Cl, but they're 2 R groups. So, and if it has 2 R groups, it's a secondary carbocation, which is less stable than the tertiary carbocation. So we could cross that out. Now if you look at D, it's a very similar case to A. So it's CH3, CH, double bond, CH, and Cl. Yeah, okay. So now we could just eliminate it because it has 5 hydrogens, but also because of this double bond as I explained earlier with A. And this structure here, if it was like that, it could be a secondary, but that's beside the point. That's also incorrect because it decreased, the amount of hydrogens in D decreased, and the initial amount of hydrogens in propene, which is required in the question. It has 6, while D has 5 hydrogens, and that doesn't make sense because we're adding HCl, and we're not taking a hydrogen away. So now going back to B, just trying to summarize this explanation. Well, let's compare B and C actually to have a better understanding. Okay, so this is the carbocation here. It's bonded to 2